Applications of quantum tunneling. Quantum tunneling is one of the most fascinating and counterintuitive concepts in quantum physics. It describes a phenomenon where particles, such as electrons, can pass through energy barriers that would be impossible to cross in the classical world. Imagine trying to walk through a solid wall. In the everyday world, this would be impossible. However, at the quantum level, particles like electrons can tunnel through such obstacles due to the strange rules of quantum mechanics. The concept might sound abstract, but quantum tunneling is more than a quirky theoretical idea. It has numerous practical applications that have changed technology and scientific understanding in significant ways. Let us explore how quantum tunneling plays a role in various fields, from electronics to biology. One of the most well-known applications of quantum tunneling is in the scanning tunneling microscope, STM. This powerful tool allows scientists to see and manipulate individual atoms on the surfaces of materials. The STM works by bringing a sharp metal tip extremely close to the surface being studied. Due to quantum tunneling, electrons can jump between the tip and the surface, creating a tiny electrical current. By measuring this current, scientists can map the surface at the atomic level, giving us detailed images of the material's structure. STM has been crucial in advancing nanotechnology and materials science. Another major application is in the transistor, which is a key component of almost every modern electronic device, from smartphones to computers. Quantum tunneling becomes important in transistors when they are made extremely small at the nanometer scale. In such small devices, electrons can tunnel through the thin barriers between different materials, affecting the behavior of the transistor. Although this tunneling can sometimes be an unwanted side effect, it also opens new possibilities for designing ultra-fast and efficient transistors in future electronics. Quantum tunneling also plays a role in semiconductors. These materials are the foundation of modern electronics. Semiconductors control the flow of electrical current in devices like diodes and solar cells. In a diode, for example, quantum tunneling helps current flow in one direction while blocking it in the other. This property is essential for converting alternating current AC to direct current DC in many electronic devices. Quantum tunneling is also key to improving the efficiency of solar panels, allowing better energy conversion from sunlight to electricity. The phenomenon of quantum tunneling is also responsible for an essential process in nuclear fusion, the same process that powers the sun. In fusion, atomic nuclei combine to form heavier nuclei, releasing an enormous amount of energy. However, these nuclei normally repel each other due to their positive charges. In stars, quantum tunneling allows these nuclei to overcome their mutual repulsion and fuse together, even though they do not have enough energy to do so based on classical physics. Understanding this process has helped scientists study how stars produce energy and has also influenced research into nuclear fusion as a potential energy source on Earth. Quantum tunneling is also vital in alpha decay, a type of radioactive decay where an atomic nucleus emits an alpha particle, 2 protons and 2 neutrons. In alpha decay, the particle must overcome a strong nuclear force to escape the nucleus. According to classical physics, this should be impossible because the alpha particle does not have enough energy to escape. However, thanks to quantum tunneling, the particle can tunnel through the energy barrier and leave the nucleus, leading to the radioactive decay we observe. This process is important in nuclear physics and has applications in nuclear energy and medicine. In the field of quantum computing, quantum tunneling could be used to develop new types of processors. Quantum computers rely on principles of quantum mechanics, such as superposition and entanglement, to perform calculations much faster than classical computers. Quantum tunneling may enable qubits, the basic units of quantum information, to perform faster and more complex operations by tunneling through barriers that would slow down classical computing systems. Quantum tunneling also has surprising implications in biology. For example, it is thought to play a role in the process of enzyme reactions in cells. Enzymes are proteins that speed up chemical reactions in the body. Some of these reactions are so fast that classical physics cannot fully explain how they happen. Quantum tunneling provides a possible explanation by allowing particles like protons or electrons to tunnel through energy barriers, speeding up the reaction. Understanding this process could have applications in biochemistry and medicine, including drug design and biotechnology. Quantum tunneling may also be involved in the phenomenon of photosynthesis, the process by which plants convert sunlight into chemical energy. In this process, energy from sunlight is used to move electrons between molecules in the plant's cells. Some scientists believe that quantum tunneling helps these electrons move more efficiently, contributing to the plant's ability to capture and store energy. By studying this, researchers hope to improve artificial photosynthesis systems for clean energy production. Another exciting application of quantum tunneling is in quantum cryptography, which promises to revolutionize data security. Quantum cryptography uses the principles of quantum mechanics, including quantum tunneling, to create secure communication systems that cannot be hacked by conventional means. This technology could greatly enhance the security of sensitive data transmissions, such as financial transactions or military communications, making them virtually unbreakable. One intriguing area where quantum tunneling could be applied in the future is in space exploration. Some researchers are studying how quantum tunneling might be used to develop advanced propulsion systems for spacecraft. These systems could potentially harness quantum tunneling to reduce the energy needed for long-distance space travel, bringing us closer to the possibility of interstellar exploration. Quantum tunneling is also influencing the development of quantum sensors. These sensors are extremely sensitive devices that can detect even the tiniest changes in their environment. For example, quantum tunneling is being used in magnetometers that can measure incredibly small magnetic fields. These sensors could have applications in fields such as medical imaging, where they could detect subtle changes in the brain's magnetic field, or in geology, where they could help locate mineral deposits deep underground. In summary, quantum tunneling may seem like a bizarre and mysterious phenomenon, but it has many practical applications that are transforming various fields. From electronics and energy production to biology and space exploration, quantum tunneling is helping scientists push the boundaries of what is possible. As our understanding of quantum physics continues to grow, the potential for new applications of quantum tunneling will likely expand, leading to even more exciting developments in the future. If you found this video helpful or interesting, please give it a like and subscribe to the channel for more content on fascinating topics like quantum physics and its real-world application.